So I'm redoing that. Um, you know, since last time, if I do that, you won't see shit. I'm pretty sure. I'm just gonna check Twitch if it's solved or not, but I doubt so. So you probably see nothing here. Let me just check real quick if I can. Yeah, if I can. You guys see nothing, so I'm gonna have to do the slideshow like that. It's a shame, but well. Okay. So yeah, I'm gonna talk about fractal upper bound for the ice of R. The function which gives a number of Eisenstein non-integers of norm less than or equal to R. So what the fuck does that mean? Um, so I'm gonna do this point by point, I guess. I hope I can do that sort of. So, what are complex numbers first off? Well, these are numbers of the form x plus yi, I mean y times I, for real and x and y, with I squared equals minus 1. It's called I because it's the imaginary number, because it's not a real number. That's why. Even if it's actually used so much in in every fucking science ever. Well, um, one thing though, with the imaginary numbers is that they like how to say that there's only one pair of reals x y such that um, x plus yi equals that complex number. Like for each complex number, you can see the thing here. So basically, you can plot every single complex numbers on a two-dimensional plane, which we call the complex plane. And you could put the real part, which is x here, on the horizontal axis or the x-axis. And the imaginary part, which is y here, not yi, just y. Okay, it's just y. So the imaginary part, you could put it on the y-axis. So I'm just gonna remove all this. I can't. Okay. So I have to get back on Google. Here we go. Okay. It was this one. Okay. Try to be as horizontal as possible. Good enough. Not good enough. I'm gonna do a bit more bigger. Okay. Here we go. Okay. So the thing is, the distance of a complex number z, so any complex number z, its distance with 0 plus 0 I in the complex plane is called the norm of z. So that explains that bit at least. So yeah. And we notate this norm as that. So the absolute value of z. But it's just trivial, we won't actually use whatever. But just for the sake of it, here's how you calculate, how you compute the norm. Oh, the norm is basically like, let's take z1 here. Its norm is just the length of that vector, because here it's supposed to be 0 plus 0 I. It's the same thing. It's just 0. So that distance, of course, is basically just so you have the real part here. I mean, how do you say this? It's basically the hypotenuse of this square triangle. If that's all it's called, I'm pretty sure it's called like that in English. So yeah, it's a square triangle, and this is the hypotenuse. The norm is the hypotenuse of it. Here, this is just the real part of z1, so 2.5. Okay, and there it's 4.5. So here the norm is, notate this as such, and it's equal to this bit, so 2.5, then this bit, so 4.5, and then we square all of it and add them up. And here we go, we have the norm. So yeah, we have the norm of z1 is just that. By Pythagoras theorem. I'm not sure how it's pronounced. But yeah, here we go. So let's keep on moving. So that was just a little introduction. So Eisenstein integers, which are those boys, or complex numbers of the form a plus b omega, with omega equals that thing, as well as a and b being integers. So, of course, Eisenstein integers are not actually integers, despite their name. Actually, they're just complex numbers. But because of their integer components, they're still called integers for some reason. A bit like the Gaussian integers, they're just, a plus bi, so it's still complex numbers, but yeah. So one particular thing they have is that they generate an equilateral triangular lattice of the complex plane. So basically, if you plot them, as you can see, there's all of those equilateral triangles and stuff. The Eisenstein integers are all the vertices of each things. Zero counts. Zero counts. Don't worry about that. Okay, so let's see some examples. Just real quick. Okay, let's see some examples. So we have the actual integers, which are Eisenstein integers as well. You just need to put b here equals 0. That works. Then we have all the integers multiplied by I times square root of 3, which we can sort of see here at least, like square root of 3. I mean I times square root of 3. Over 2, yes, but basically if you put b equals, what will it be? It's equals 2a. If you have b equals 2a, you would have b, the real part will be a minus 2a over 2, so a minus a 0, and the imaginary part will be square root of 3 times times 2a rather, all over 2, so it's just a times square root of 3, so any integer times square root of 3, so yeah. And then we have the norms that Eisenstein integers can have. So basically, we can base ourselves on what those, like those examples of Eisenstein integers have as norms, and we will have already a good bunch of what norms Eisenstein integers can have. So we have all the natural numbers, of course. These norms are, always positive. So basically, if you do the norm of a real number, it's just going to be the absolute value of that number, and the absolute value of all integers give all natural numbers, So, the norm of -1 will be 1, norm of -2 will be 2, norm of minus pi will be pi, and the norm of pi will be pi as well, so stuff like that. Natural numbers multiplied by square root of 3. Again, it's just because of that, except instead of going this way, and doing the absolute value on the horizontal axis, you do it on the vertical axis. So yeah, still you just need to remove the I, so like that, and then do the absolute value. So it gives you precisely that. But these are not all the possible things you could have. You can check here. We only did those ones with the natural numbers and stuff. Those we can have a norm of natural number multiplied by square root of 3. Like some of them at least are on the vertical axis. There are some more, but you need to show they exist, so yeah. But here's the whole set. It's the set of square roots of Lorentzian numbers. And this gives you all the norms that Eisenstein integers can have. So you can check the OEIS to find out this sequence and how they're defined. So basically, Lorentzian numbers are natural numbers of the form x squared plus xy plus y squared, with x and y being integers. So it gives you that weird thing. Yeah. So yeah. Then here's the problem. So the number of Eisenstein integers there are with norm less than or equal to r for is called ice of r. So now we have explained basically everything here, except that part, but it's gonna come up for later. So we have explained all of this part already. So yeah, but here's how you could geometrically see this. So geometrically, you can calculate ice of r by drawing a disk of radius r centered around 0 plus 0 I. in the complex plane and counting how many Eisenstein integers, which are just vertices to all the triangles here, or contained within the disk. So, for example, if I do like r equals 0, there's just going to be that. Anything from r equals 0 to r equals 1. This is just going to be one vertex or one Eisenstein integer. If we like put the radius up to 1 or above, we're going to get 1, 2, 3, 4, 5, 6 more than the precedent, than the previous count, which was 1, so 7 overall. So 7 vertices, and then if we go up to square root of 3, which is roughly 1.73, if I'm not mistaken. Yeah, so there's this one, this one, this one, this one, this one, this one. So 6 more, which is like 7 plus 6, 13. So we have 13 vertices. There's where is it? Okay. There is a thing that counts the difference. I mean, how many stuff there are each time, but basically, I don't give a shit about this one. I'm just gonna put this one instead. So we had like 1, then 7, then 13, if I'm not mistaken. So it's actually called the sizes of clusters in the, well, they call it the hexagonal lattice because, well, you can see there's some hexagonal patterns and stuff. But, well, it also works as a triangular lattice in a way. But I guess there's just only one way to make an, a hexagonal lattice. I'm pretty sure that's why they call it like that. So, but yeah, here's the whole list here for you to enjoy. So yeah, but the thing is, there is no exact formula for height of R. Just as there's no exact formula for the nth Lushan number. It's not a thing, and you will need a formula for the nth Lushan number to actually give this. Yeah. So there's no exact formula, which can be a bit faster than just brute force it. So yeah, it's not very terrible. But yeah, we can try to find an upper bound though, which is accurate enough to be this one. So, how could we find an upper bound though? Well, we could maybe simplify the problem first. So, let's tile the complex plane with squares instead of triangles. So, we would have this. See, just squares. And yeah, you just do stuff with with the circle, or with the disk rather. Yeah, and we'll count the Gaussian integers, which are just the vertices of this. You can check the Wikipedia article to inform yourself on what Gaussian integers are. Yeah, these are just like 3 plus 2i. I don't know why it's always this one which is always used for some reason. For every fucking visualization, it's always 3 plus 2. It's weird. Anyway, so yeah, we could ask ourselves how to upper bound the number of of Gaussian integers. Yeah, for this case. We could ask ourselves how many there are within the circle, or how many there can be, rather. So we would love to, upper bound this some way or another in a, in an easy fashion, at least. Easiest, and basically the easiest shape for me to count how many stuff there are in this shape is probably the square for me. So we're gonna inscribe this circle in a square and try to work out stuff with this. See, now I've inscribed this circle within this square. Okay. I'm just gonna yeet that. And now we're gonna analyze a little bit. So, if the square is of side length 2, yeah. So 1, 2, yeah. How many Gaussian integers are within the square? We include the borders, by the way, just so you know. It's also the case with the circle. We include the borders. So we have 1, 2, 3, 1, 2, 3. So 3 squared. Okay. We can even try with r equals 0. It's just gonna be 1 because there's 1 here. So it's gonna be 1. Then we're gonna go up to 2. There's 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So 5 squared. There's 5 squared Gaussian integers here. Then 3. Okay, let's do that. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay, so 7 squared, etc., etc. I think you can catch something here. Here there's 1, 2, 3. 1, 2, 3, and the middle one on this side. Okay? Yes, there's 1, 2, 1, 2, and a middle one. So basically, on each side there's 4 plus 1 stuff. You can see 5. We do 3 instead. We have 7. So it basically works. And since we square it, because it's a square literally, it's gonna give us this formula. Okay. So technically we could do that, but as you may see, this I mean, if you have r equals 0 up to r equals 1, I mean, if you increase r, these shouldn't decrease. They should just jump from 1 to 3 once r, passes 1. But the thing is, it actually gradually increases from r equals 0 to r equals 1. But there's no new points. This is completely stupid. Why would you increase the thing when there's no new points anyway? So one way you could do that, one way you could solve this issue, is doing the integer part of r, which is just floor of r for positive reals at least. And we just care about positive reals for this sake, so we could just see this as the integer part. So basically from r equals 0 to r equals 1, it will not gradually increase anymore. It's just going to be 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, and then once we go up to r equals 1, it's going to be 9 because it's 3 squared. And boom, 3 squared, 1, 3 squared, 1, 3 squared. So it has a very simple counting property. But the thing is that um, here each individual, Gaussian integers or vertex have a distance of, I mean, with its nearest Gaussian integers, uh, it's gonna be of distance 1 on the x-axis, or on the real part axis, if you prefer, um, and 1 on this axis as well. But here it's a bit more complicated. Here for each Eisenstein integer, its closest, I mean the closest Gaussian integer, sorry, Eisenstein integer um, to each Eisenstein integer is going to be of distance 1 on the x-axis, just like here, but it's going to be of distance square root of 3 all over 2 for on the y-axis. So yeah, it's a bit squished. It's gonna look a little bit like that instead. But also it's gonna be a bit tilted. So to to talk about the tilt, I'm gonna do from 0 to that. Or yeah, we could do that maybe. We're just gonna let it run because it's maybe better. Okay. So let's say it's so weird. No, I'm just gonna fix it at 0.5. Okay. So we've tilted our thing a little bit. So here's the catch. I'm gonna remove that real quick. So I'm just gonna look on that, yeah. On the horizontal axis because it's still, 1 unit, 1 unit, 1 unit. It's just gonna be very simple. So I'm just gonna look on the x-axis first. You might see something once I get to r equals 0.5. Just gonna increase it a little bit. Here there are two things, but our upper bound says there's only one thing here. Is it not accurate? It is not. It will be that instead. Because when we do that, we actually do twice r, so the integer part will actually, increase every 0.5 steps instead of every 1 step. And because, we tilted our thing, so it's, 0.5 plus 0i of center, Thing is, it can only, get to 2 or basically it increases at this point here. So I don't know how to say that, but yeah. Anyway. Oh, I'm really bad at explaining stuff. But yeah, basically, one way we can fix that is just, pull the 2 from the exterior to the interior. And it gives us that. which is pretty fucking accurate, to be honest. Now we're gonna try to do this on the y-axis. So one stupid way we could think of this, um, which might work, of course, but it could be, like copy pasting this and dividing by, well, square root of 3 over 2 because it's, stuff like that. Um, so yeah, it might work, but the thing is, it's not gonna do the job. 1, 2, 3, 4, 5. Oopsie daisy. Did I really just do that? Okay, so I'm just gonna rewrite that real quick as such. So, what about we do that, which is the same thing, but instead, first off, I have to tell you all that because it's the integer part, if you pull the +1 inside the for function or the integer part function, it's gonna stay the same thing. So you can put it inside. I'm gonna do this here too because otherwise I can't simplify. Okay, so what if we did exactly what we did with 2, like putting it in the for function, but with this, with this, and you pull it inside. So let's do that. So we have that, okay. So I'm gonna simplify it real quick. Okay, so now we have 5, which is accurate for once. So yeah, there's 6 here, but well, why not? And to be honest, there should not be any, shenanigans with tilts and stuff. Just gonna check, but normally, yeah, it should be okay. Yeah, it's pretty much okay. Yeah, okay. So yeah, we have our thing. So we have a sort of this and this, which you could multiply together to give the number of Eisenstein integers there are, or sort of, but well, or actually an upper bound of how many there are. And here it will give you 9, so yeah, that's cool. Here it gives you 30, apparently. 1, 2, 3, 4, 5. Wait, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yeah, it should be 25, but because it's an upper bound, it's gonna be higher than 25, which it is, so yeah, all works good. And because we took account of all the tilts and stuff, this actually will do the job as a as an upper bound for this, for EIS of R. So next the diapositive, we just have that, which is, as I said, just this product here. So yeah, we naturally have an upper bound like that, but thing is, there's still room for improvement. Well, okay. So let's just check in something. Okay, So there's still room for improvement. Like there's still a lot of space between the circle and the square. Um, like, oh, funny enough, I forgot the square. I'm dumb. Oh shit. Do that. Okay, I'm gonna put the same color. Okay. Okay. So what was I saying? Yeah. Okay. So this should give us a good upper bound and stuff. And yeah. So there's still a lot of space between the circle and the square. We may want to fill that up somehow. So yeah, you can see there's still a lot of space um in those areas, like here, 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 no, here, stuff like that. So we might want to fill I mean, those things, up. Just saying. Uh, yeah. And then it will be better if the upper bound you get it actually works both for small and large values. So if you think of dividing the square in equal bits, and just basically like how could you say that? Like dividing the square in equal portions, like like if it's a grid or sort of, and then you would count how many Eisenstein integers there could be here, 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 and stuff. And when it touches the disk, it's not counted and stuff like that. You will subtract all of this, then you'll subtract all of the shit from the from the upper bound and stuff. But the thing is, it's gonna be a bit complicated, and it's not gonna. I mean, if it works for small values, it's not gonna work for large values, and so it goes the other way around. If it works for large values, it's not gonna work for small values, and even worse for large values, it's gonna work only on a certain range of large values. But if it's below, it's not gonna be accurate. If it's bigger, it's not gonna be accurate at all. It's gonna be way off. So we might want something else. Here's my method. Binary fractal of squares. So what do I mean by that? Start from the upper right corner of the square. Okay, so I'm just gonna zoom that real quick. I'm gonna. We don't need the whole thing anyway, so. Okay. So, as we said, we start from the upper right corner here. Okay, so what do we do? Draw a square from this corner to the nearest point to the corner on the circle. Okay, so I'm gonna draw a square, but I mean, you could draw a square like that, fine, but I'm not gonna do that. I'm just gonna draw a diagonal first. Gonna put it this way. Yeah, you can't see it, it's normal. Okay, so I'm gonna draw that with only two segments. So the explanations will be better then. So, from this, what you do, like you take the outward edges. So what I mean by outward is the furthest to the radius, to the center of the circle. So the two ones here and here. So yeah, the outward edges of the two segments. That's what I said. So with the burgers and make two squares with these as their upper right corner. So we're gonna make two squares for which the upper right corner is this one and the other one is this one. So, but what's the other corner? The nearest point on the circle has their bottom left. So we're literally gonna do the same thing. Okay. Ah, it's a bit complicated. Oh shit. And for this one as well. Okay, here we go. So we do that. Okay, we have that and that, and now we have a new bunch of squares. And then you repeat the latter step for each new square. So basically, take this corner, and this corner, take this corner, and this corner, and you're gonna do diagonals and shit, like that. And then boom, you do a square. Then you do a square here as well. Do a square here, sort of. Gonna do a square here. I'm bad at drawing squares. And stuff like that, you know. And then you're gonna repeat the process. Boom, 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 etc., etc. So it's gonna look a little bit like that. Wait. I should probably move that and put a bit less stuff as well. Put like depth 8. No. It's not gonna be a lot, but yeah. So yeah, it will look a little like that. So I guess you can see why it's called a fractal. Because it is. So yeah. We have all of this. Which fills up the the space between the square and the circle, or at least a quarter of it. But if you do 4 times all the stuff you need, it's gonna be okay. So what we need now is wait, I'm not sure if that's what we're gonna do now. Oh yeah. Then you can report the side lengths of each squares drawn in an infinite binary tree. So what do I mean by that? So let's start from this thing, okay? And I'm gonna label it with the length of the square which is generated when you do that. So the side length of the thing. It turns out it's this. So, but of course I don't forcefully. I don't know all the others actually. So Yeah, it's just that this one here is actually that. Okay, and then I'm gonna take this one and this one, which are generated from this square here. So yeah, so I do that, and then I do that and do that. So I'm gonna take this one, so this one, and this one, okay? And I'm gonna report the lengths of the squares which are made. So it's gonna be this one, like L1 maybe, and here it's gonna be L2, so L2. And then you could do the same thing over and over again with these corner, these corner, these corner, um, so these corner I said, these corner, etc., etc., and you can actually do a binary tree with all the lengths of all the things and stuff. It's actually how I interpreted it so that I could got the animation you can see right now before your eyes. So it's how I interpreted it, such as a sort of binary tree. Um, it's actually a very useful way of seeing things, especially if you want to map it. I mean, if you want to, let's say this, make a function from 0 to 1, I mean, in the range 0 to 1, but without 0 and 1. Such that you can map every dyadic fractions. So just gonna real quick. Actually, well, I can just explain it what it is. So a dyadic fraction is a fraction which is um, an odd number divided by a power of 2. So for example, 2/3 are not a dyadic fraction because it's 2/3 and 3 is not a power of 2, but 1/4 is a I mean it's something odd over a power of 2, so it works. Stuff like that. So this is what a dyadic fraction is, and basically they can be listed as 1/2, 1/4, 3/4. I mean between 0 and 1 at least, without 0 and without 1. They can be like drawn like that. So 1/8, 3/8, 5/8, 7/8, sort of. I don't know why I linked these two together. Okay, so basically, if you do L of this, it's gonna give you this, which is 1 minus 1 over square root of 2. If you do L of 1/4, it's gonna give you L1. You L of 3/4, it's gonna give you L2, etc., etc. I guess you can see how we can map both things with each other with a sort of map L, L with which basically stocks the lengths from dyadic inputs in a way. And yeah, that's literally how we defined L. And I know I explained it very, very late, but actually, I can explain it late here too, but not as late as last time. Um, here, the radius of the thing, of the of the circle, is actually 1. Okay, so we just normalized everything, so it's 1. But if you want a circle of radius r, it's going to be all of these lengths times r. Okay, because all of these calculations are made with r equals 1, and since it's linear and stuff like that, you can just do the length times r. So it's gonna be like all of x times r, with x being a dyadic fraction between 0 and 1, strictly between 0 and 1. And it's funny because if we look at the plot of 1 over L of x, I mean, it's not funny because, of course, it's you know, it's arising from a fractal boy, or rather, a fractal boy like that. Since it arises from this, I guess you could guess that function would look like a fractal or have a sort of fractal structure. But yeah, here it is. It's only 13 iterations. I don't remember. 12 or 13 iterations here. That's not a lot, but yeah, that basically looks like that. There's a lot more stuff like that if you do more iterations, but yeah, it's very self-similar and stuff like that, so it's pretty cool. It looks nice. um, and it's actually useful, so that's cool. Anyway, so here's how we're gonna subtract all of the squares contents. So we may want a lower bound of the number of Eisenstein integers in any square of a specific side length of a specific side length, or the since we're subtracting it from an upper bound. Anyway, please, there we go. So there's a sort of visual cue. So on the bottom, like here, there's stuff which are of distance square root of 3 all over 2 apart, and on the bottom there's stuff which are just 1 apart to each other. So yeah, and you can see it changes color every time. You can actually tilt those as such, and basically this thing can be used, to find the upper bound of how many times, there's stuff that changes here times how many times there's stuff that changes here. Basically, that changes colors, and that's equivalent to our problems because once we do the product, it's going to give us an upper bound. I mean, if we do the upper bounds, stuff like that. And yeah, you can try to see stuff with the length and stuff. So we don't really care. But the lower bounds, though, here's what I got. Floor of R and floor of 2 over 3R. They are very, very basic ones, but they still work. So here you can see it says that there's 0 thing. Because if we tilt like literally to anything other than 0 or square root of 3 over 2 on this slider, you can see there's like nothing. There's no change whatsoever. So it's reasonable that the number of stuff there is on, the number of changes there is on this of this line versus the ones that are on this side, on this thing. um, it makes sense that there's nothing particular. Also, I actually only care about this half of the segments, not the whole thing. So I'm just going to tilt it a little bit. Yeah, I mean shift it a little bit. Um, so here it's reasonable, but then, you know, here, oh yeah, we have to untilt this. So you can see the extreme cases. Yeah, the extreme case is this one. You can see that it counts only one thing here. Um, for now at least. So it counts only one thing here, but it still counts nothing here, despite, you know, if you shift a little bit, it's cold. There could be something, but yeah, it's not forcefully the case. And it's a lower bound, so technically there could be this one, but it's not counted. And then we just reach one and everything is one and stuff like that. And yeah, so basically it only increases like every 2 over square root of 3 for this one and every unit here. So I mean for this one and stuff. So their product gives us a lower bound for each square. Yeah, it's a bit complicated to explain. I could put the content here. Yeah, if you want to play with this. So uh, basically, we have to do like this times this, except we have to, you know, remove all and replace this by all of every single fucking thing that all can be. Um, I mean, every single thing in its domain of definition, which are dyadic fractions between, I mean, strictly between 0 and 1, times all. So not just all. So basically, yeah, it will be our first our first upper bound, which was um, this. That's how we write floor, by the way, in general. But yeah. Um, so that. Then what we do is we remove 4 times the floor um, of L something times R over, oh wait, this times something. Okay. To be a bit more precise, we need to actually do a sum of all of those. Yeah, so it's gonna be so let's imagine we have x in the dyadics. So we have x dyadic 0 x. Okay. Then we would have this because it's every possible value of x basically. So, that you know for which L is defined at least. So yeah, we have all of this. So I put this here. I put this right here. Okay. And therefore we have EIS of R less than or equal to that. Yeah. That's not exactly how I wrote it. I had to do a double sum, but basically this is the simplified version, which is not simple, but it's a bit more easy to read than this mess, even though there's just a double sum except of instead of a single sum here. Um, and yeah, so it basically looks like that, and that's the best bound I found. Uh, it's pretty accurate. Um, do that. So, for example, at is it the right one? At least I'm just gonna check real quick. Yeah, so the right one. So at 500 and wait, at 12 actually. Um, like it's gonna upper bound 517 by 700. It's not that bad. Honestly, it's not that bad. Um, especially when you check this. So, what this graph is, on the black thing, there's ice of R. So it's just a tiny bit. All the rest here in light blue is an approximation of ice of R. A very good approximation. It's 2 pi times R squared, all of it square root of 3. But, you know, sometimes it's above ice of R, sometimes it's below. It oscillates every time, so it's not very reliable as an upper bound, or whatever. But here's like the red line here is R upper bound. All these things, by the way, are the square roots of all of these because they have a square growth, so they will be way off the charts, you know, if I didn't do the square roots instead. So they look like that when we do the square root, and honestly, it's like they're really close. You can see how close they are. Like it seems that it gets, I mean, the red line, which is our upper bound, seems to get, bigger and bigger, like in a constant rate, but like it's so slow, and actually it's as slow as possible so that, you know, um, it's not as slow as possible. What am I saying? But the thing is, these two lines here are asymptotic to each other, which means that if you do the ratio of one and the other, what you will get for R tending towards plus infinity will probably be 1. Actually, it's not probably, it will be 1. So yeah, if you do the upper bound all over ice of R, or all over 2 pi r squared over the square root of 3, either of those anyway is gonna tend towards 1. Uh, so yeah, it's a pretty good upper bound since it's literally asymptotic to the thing it's supposed to bound. So yeah, it's a good upper bound in this sense, but there's still a big O of n error, I'm pretty sure. I didn't do a lot of asymptotic analysis on this, but I'm pretty sure it's ON, O of n, if people know what it is. So, meh, but it's still quite good. Still quite good. Um, but if someone finds a better way, a better, way to count how many there are, that would be awesome, obviously. I know these are slightly, related to the series of the A2 lattice and stuff like that for people who know what it is. I'm not really good at this. I'm more of an analytic guy, as you might see. So yeah. Anyway, that's all. That's really all. So thank you all for watching, and special thanks to Christian Bolton for asking me to find a solution to this problem, which was finding an upper bound which is accurate enough to be used. So yeah, it's a very fun problem to tackle. I invite you all to find your own upper bounds and stuff like that. Uh, that's all. That's really all. So thanks a lot for watching and for tuning. Yeah. Uh, yeah. Thanks.